I'm thrilled to have been volunteered to talk at altitude again. Because this talk's about IPv6, and I gave a talk last year, and my one statement about IPv6 last year was that no one cares about IPv6. In hindsight, poorly chosen words. Because this year, we now have IPv6 in limited availability, so now I have to sell this idea. Oh, someone does care. Okay, you're wrong. If you know nothing about IPv6 and the Internet Protocol, the one thing you need to know is that in a computer network, in order to communicate with other nodes, you need an identity, and effectively that identity is the IP address, right? The other thing, so in addition, the IP address, in addition to being who you are in the network, also has another interesting aspect, which is that in order for nodes to know where the other identities are, they need to be able to forward packets. And they do so by effectively aggregating identities into prefixes and doing longest prefix match forwarding, right? And so in addition to being who you are, somehow it conflates this thing about who you are in the network and also where you are, right? And this is a very bizarre conflation of things. It's not how you'd probably design it. But what you have to understand is that IP kind of starts as a toy model. It wasn't never supposed to be this successful, right? And compared to all the other networking protocols, it was way simpler, so no one expected it to survive. And really starting from 1974, people just started tinkering with it. But it was easy, and you could build it yourself, and you could just connect to the network, and you were done. And so over time, the network grew, and it kind of completely transformed into something else. Because businesses started connecting, and it was valuable all of a sudden, right? And so by 93, 93 is kind of a pivotal year for internet addressing, because a bunch of things happen. The first thing that happens is that in January of 93, the first web browser gets released, right? And this freaks people out, because up until this point, we thought email was a killer app, and that was popular. And all of a sudden, this comes along, and it changes everything. And the general feeling was that IPv4 was never going to scale to deal with this, right? And so as a reaction to that, the IETF, the standards body, created a task force called IPNG. And IPNG, the charter was pretty simple. It was essentially to scale internet addressing to the millions of designers needed to fix the Mosaic logo. And they started work immediately. And so within 3 years, IPNG created a protocol, and it was IPv6. This 3 years is an extremely short time if you compare it to the amount of time we tinkered and played around with IPv4, right? And so IPNG, as a task force, they had lots of good ideas, right? These were the brightest minds in networking. But unfortunately, they needed something deployable, because the perception was that the whole internet is going to implode any minute now, right? So effectively, we implemented none of them. And so IPv6, effectively, the only change you need to care about, the only one that actually matters, is that addressing went up from 32 bits to 128 bits, right? The other thing that happens in 93, though, is that we actually fixed the addressing problem. Two things happen. One is that we deployed classless interdomain routing, and that's just a more efficient way of aggregating prefixes. And the other thing is we accidentally discovered network address translation devices. Ironically, someone in the IPNG. And effectively, those devices, well, they just partition the network into private networks. And now you can reuse an identity in different private networks, and your public identity somehow becomes just the IP of your NAT box to the rest of the network, right? And this has scaled the internet beautifully until now, for the most part. And so really my statement about no one caring about IPv6 is most of you don't actually care about what network protocol your traffic goes on. Effectively, you care about higher order properties like performance and reliability. And effectively, IPv6 offers no more benefits or disadvantages compared to IPv4, right? Because by design, it's pretty much exactly the same. But there are a few people who care dramatically about IPv6. And the first class of people are network engineers. Network engineers mostly care because of the novelty factor, I would assume. Because in the time it's taken to deploy IPv6, we've had 2 major versions of HTTP, 4 major versions of HTML, and tens of thousands of JavaScript frameworks. So you can empathize that this is a big moment, and probably the last network protocol change they'll ever see in their lifetimes. The other big group that are really pushing IPv6 are effectively companies where addressing sucks. This is a class of company, by the way. And so you'll hear a lot about big push for v6 effectively from companies that operate data centers, right? If you have hundreds of thousands of devices, IPv4 was never designed to work for you in the first place, right? And so this gets very complicated. The other set of users that really drive IPv6 adoption right now are mobile carriers. They have a similar kind of setup to data centers in that they have to operate hundreds of thousands of devices potentially, but they have the additional difficulty that these devices are mobile and they're like moving around, and now you have to grant and revoke IP addresses. It's hard, right? These are really, really hard problems, and like I feel for them. But at the same time, I'd feel a lot more if they paid us money. And so, like, our job is not to actually help others manage their devices, right? Our job is to deliver traffic. And so if we're going to adopt IPv6, it better fix all our problems along the way, otherwise it's not really worth it on our end, right? And so the way most people do this, in transitioning from v4 to v6, is that they take all the concepts you have in v4, and then just map them directly to IPv6, right? But IPv6 is a much larger design space. So this doesn't actually make sense because you might actually miss all the other possibilities you could have done, right? And you'll never even find them, potentially. So when we started this about 2 years ago, we made a strict decision that actually we were going to do the exact opposite, right? That we were going to start in a design space and figure out what would work and what wouldn't, and then somehow map it back to our existing reality, right? And hopefully find new stuff along the way. And so we started. So CDNs, from an addressing perspective, are extremely simple to reason about because effectively you have clients, and clients issue requests, and then you have points of presence, and points of presence just process requests, right? Now, the classic model of a CDN, in terms of addressing, is the Unicast model. And this was pioneered by a CDN in the late 90s. I don't leave much to the imagination because there's only one. So, arguably, they're still there. And so, your words, not mine. And so, like, every POP has a prefix announcement, and that's that colored label thing, right? That's fine, and then DNS gives you an IP address, and an IP address is composed effectively of the prefix concatenated by some offset. And then that will route directly to a specific point of presence, right? Because that announcement is only coming from that point in the network. And this is great. All the routing is done via DNS, right? Effectively, you can give out another IP, and that will route your request to another point of presence. Now, the problem with the Unicast model is if your point of presence goes bust, right? Because now you have all these things pointing at a point in the network which effectively can't even serve traffic. So that sucks. The other problem, however, is that it's incredibly easy from a denial of service perspective to target individual points of an infrastructure. And so you can imagine that if you just send a truckload of packets to a single point of presence, it's effectively going to fall over eventually, right? And so in contrast to the Unicast model, about 10 years later, the Anycast model starts gaining popularity. And Anycast is an extremely simple concept. It's just the idea that you announce the same prefix from multiple places. Prior to this time, you couldn't really do Anycast reliably with TCP. It requires a certain maturity of routing protocols and mostly routing code. And so CDNs cropping up at this time start using Anycast instead, right? And this DNS functions exactly the same. It gives a prefix, an IP address, but this time an Anycast prefix concatenated with an offset, right? The difference is that the network decides where traffic ends up. And this is according to arbitrary network policy and network distances, right? The problem with this is that someone somewhere is going to screw this up, right? And there's always some network device somewhere that decides that here's a network announcement from elsewhere, and it's a really, really close path, and so it decides to take it. And that's how a request ends up in, say, Sydney, right? And so the Anycast model is really popular because you don't need much IPv4 address space to do it, right? Like, anyone can announce Anycast prefixes and call it a CDN. And it also has this innate ability to gracefully handle DDoS attacks. The only problem is it's impossible to control, right? You will get 90% of the time the network will do the right thing, and then the remainder of your existence will be an uphill struggle trying to tune the rest of traffic to go the right place. If your core business is being a CDN, Anycast is not that great a solution because the 99th percentile is very hard to maintain, right? And so Fastly, when we started, we were a Unicast network. By 2014, we had a Unicast network and an Anycast network because some customers actually need Anycast. And so by 2015, we start implementing IPv6. And we originally start with the idea of a backing Anycast, right? This is a pretty simple idea. It's the idea that you announce an Anycast prefix from all POPs. But in addition to that, you announce a more specific prefix, which is subnetted from the Anycast prefix. And that prefix you announce from each POP individually, right? So here we have a prefix pointing at Sydney, which is subnetted from the Anycast prefix. And now it's simple. Everything else just follows, right? That you give a Sydney IP to your clients in Australia, and the network will forward them to the Sydney POP. The interesting thing here is that if someone decides to DDoS that particular point of presence, we can just remove the more specific prefix. And now, client traffic is effectively still routed to Sydney because it's the closest POP to the clients in Australia. DDoSes, however, will never be generated in Australia, right? You need bandwidth. And so the network will just point them elsewhere. And so you'll probably end up somewhere, say, like Frankfurt or something like that. And so backing Anycast has these nice merger of properties, right? You get the control of Unicast, and you can gracefully handle DDoSes because you can always fall back onto Anycast. So you're always serving traffic. It requires a lot of upfront investment in terms of buying IPv4 space. So it's not something that you naturally start with if you're starting a CDN. But the other thing is it still doesn't actually provide enough control. And so the case that it still doesn't resolve is the fact that providers have their own intentions, right? And so in Germany, there's a very big mobile carrier, and we exchange lots of traffic with them. There are a lot of eyeballs there. And as a result, we naturally reach out and ask to establish a direct peering connection, right? And this is advantageous for both sides because both sides stop paying for the traffic they exchange. At which point, the carrier will probably say they love the idea in exchange for money, right? This is very awkward if we have to politely refuse because we already have paid peering ports. They're called transits. And so we kind of fall back to the transit case. Now, effectively, what should happen is that we give an IP for Frankfurt, traffic goes to Frankfurt. And this is actually almost exactly the same RTT as going via peering, because all our transit providers, all the carriers, our data center, they're all in the same co-location center, right? So you're talking about almost no difference. There might be more network hops, but really, in terms of RTT, there is almost no additional delay in this case. But the providers have other ideas because they hear an announcement from elsewhere. And so they follow that path to some random route exchange point somewhere else, maybe outside the city, maybe outside the country, which happens to have been learned from a transit provider we also connect to in Frankfurt, right? And providers do this all the time, either because they have no idea what the actual performance of the traffic is, or because they do it on purpose as a form of, effectively, extortion. And so you can't really solve this problem very easily in IPv4. But we can in IPv6. So what we've effectively implemented this year is per provider addressing. And so you can think of address space in IPv6 as a large contiguous block. And this would be the Anycast prefix, right? And what we'll do is we'll separate it and we'll break it down. And so you can imagine that we have one subnet which we announce to everyone. And then we have another subnet which we actually only announce over peering links, over which are settlement free. And then we can have as many of these subnets as you want for individual transit providers, right? And so the blocks are per provider effectively, or groups of providers. And then what we do is we then subsegment these again into announcements for groups of like POPs or groups of POPs. So you might have Frankfurt announcements and Sydney announcements, LAX. You can have announcements for POPs in Asia, for example. This is kind of arbitrarily constrained Anycast groups. And the nice thing is this all falls back, right, into the larger Anycast block. So now the nice thing is that we no longer just announce these two prefixes. Things get a lot more complex because we have to start announcing more specific prefixes for all the combinations of eventual results that we want. But that's okay. IPv6 space has, like IPv6 addresses have space for this. And then via DNS, the IP we start giving out is not just Frankfurt, it's Frankfurt via a specific provider, which happens to be the fastest, right? And so you're effectively pinning connections to the route towards you that you actually want. So what's going to happen eventually is, once we go GA, hopefully, is that every service at Fastly will effectively get the service ID hashed into the lower 64 bits of the address. And so you'll end up having unique IPs for every service. But not only that, it will be combined with every possible prefix. And so geometrically, you can actually think of this really simply, because this is, despite the amount of addresses can be thought of as projections of IPv6 identifiers, so this is the last 64 bits, on separate addressing planes, right? And so the model just derives everything automatically. The nice thing about this, however, the nice thing about starting with IPv6 is that somehow we explored every single possibility we needed, and now we can start retrofitting this back into IPv4 by just connecting the dots, right? We can start mapping out different blocks to their equivalents in IPv4. Now, obviously, we can't have all of the expressiveness of our addressing scheme of IPv6 and IPv4, but we can kind of evaluate which ones actually provide the most value for our customers and retrofit, like backport those back to IPv4, right? So effectively, this is now deployed for IPv6. The nice feature about the prefix scheme itself is that it basically accounts for every possible failure mode, whether it's for POPs or for providers. It just falls back gracefully. And it turns out there's only one way you can arrange prefixes to get those properties. And it gives us complete control of ingress path, except against providers who are actively kind of acting in ill faith. But that's okay, because we can actually note who is acting in ill faith or not. The only problem with this scheme is it's really, really hard to implement, and I don't recommend anyone try it. It's just hard. Yeah, it was a long time. So the other nice thing, however, is that you can turn it around. And you can effectively apply the same concepts of geometric decomposition to other forms of addressing. And we've done that too. Because when talking to origins, we can't actually use the client-facing IP. We have to have a specific infrastructure IP that's associated to the machine that's pulling content. And so currently what we have is that we have a single site prefix, effectively, that we pull content from. And it's always on the provider side, on effectively wherever you host your content, that ends up choosing the routes. Most of our customers do not actually get to choose which route they actually select to us, right? It'll be something like AWS. And so effectively, we can now do kind of apply the same logic, although the order of the subnetting has to be necessarily different for failback reasons. And if a provider happens to be broken, we can just pull content via a different provider by changing the source address with which we reach out to you. So There's actually no Q&A in the session, but there's lots of questions that I've left open because I don't really have time to go over it. This service, I've spoken about lots of things. Most of them are implemented. Not all of them will be immediately available to you, but we're running limited availability on IPv6. And if you want to try, help us test it out. We're mostly trying to stress test it slowly and ramp up. Please reach out to anyone in the red shirts. There's lots of heartache with the amount of configuration complexity with dealing with that many addresses. And just generally like configuring multiple IPv6 source addresses for every cache, for example. And our caches now respond to trillions of addresses, which is always really fun. I didn't really talk about the way you limit impact on the global routing table. So we're announcing a lot of new prefixes, and if you don't do this carefully, you end up polluting the global routing table, which is something people feel very strongly about. But we actually do it in a way that we minimize things by doing no exports to specific providers and stuff like that. So it's actually the most compact scheme you could possibly come up with regards to total impact. And generally, there was a lot of work around how you retrofit higher order dimensionality into systems which only really perceive one dimension, right? And that was most of the work. Now, there's also, so if you have any questions, please reach out to me, I'll be around. And there are other people who also worked on this. But there's a set of questions I have been consistently asked over the last year, which I'd really love to not ever hear again. This comes normally in the form of Twitter trolls. They're like, it's great. So I've grouped this into two variants. So the first type of question is, why do you not implement feature X like company Y? Very popular. Almost always the answer is because Y did a terrible job. So like history is littered with terrible engineering decisions, normally justified by a false sense of urgency. So we try to avoid that if possible. The other question we get asked an awful lot, and this is specifically from network engineers who implemented IPv6 in other carriers normally, mobile carriers especially, which is, why is it taking you so long to get here? This question is beautiful because it's laced with confusion, right? It assumes the author and the subject are traveling in the same direction. So really weird. And so why does it take so long? Well, I don't know if it took us long at all, right? How long would it take you to redesign everything from scratch in a largely unexplored design space? How long would it take you if you then wanted to retrofit that all back into your existing architecture? And then how much longer would it take you if you had to do all that while continue to expand the breakneck speed? I actually don't know the answer to that question, but most of these questions don't actually matter now that we've arrived, right? But the point was never arriving. It was just to go somewhere else, right? Thanks.